welcome back to another session of Learning Glass Studio for this combustion class. Today we'll talk about application of mass transfer analysis, droplet evaporation rate. So droplet evaporation is both thermodynamic process and or kinetic process. If you want to know how fast a droplet will evaporate, we need to apply the mass transfer analysis we're going to talk about today. If you want to know what the stability or whether a droplet is stable at a certain condition, that's a thermodynamic question. So to apply this rate analysis, we would use these concepts of mass transfer. In this case, we'll see that it's a diffusivity process in terms of keeping track of a species across a control volume. And as we learned, that there can be some convection components of this transport from A to B, moving from one location to the other, and diffusivity contributions to keeping track of a certain species that you're analyzing. So we'll also see that there is a thermodynamic parameter in here that is needed to complete the analysis. So if we were to apply this mass transfer analysis using this governing equation of the mass conservation or mass conservation applied to a specific component of a mixture, we can have a very nice, easy to use solution with following these assumptions. If you have quiescent surroundings, meaning that there's no flow due to convection surrounding a droplet, this droplet that you're analyzing is quasi-steady. I'll describe what that means. Is that there are some things that we allow to change, but the time dependence does not change, is not affecting this. Even though things are changing, the time dependence goes away. Fixed droplet temperature that we're analyzing, and this is the thermodynamic part. You know the mass fraction at the droplet surface, which can be found using correlations between the surface and the interface, like the liquid, the thermodynamic or mixture properties of the surface of the liquid, of the droplet versus the surrounding interface, or thermodynamic analysis can be used there to find that. And then another thing that makes the math easier is this quantity of the mixture density times the diffusivity is constant. So with those assumptions, we'll start analyzing this control volume we're considering here. So this is a droplet in radial coordinates. So this would be the R coordinate. And this particular droplet has the radius of the surface as it is vaporizing. And so what we're looking at here is an evaporating droplet in spherical coordinates. Spherical coordinates, and so here in the gas you have A plus B, but the droplet itself is just liquid A. For this scenario. And since it's a mixture here, we can define at some distance away, there's a mass fraction far away from the droplet surface. And at the surface, if you know the thermodynamics, you can find this, or you can use other correlations, other mass transfer principles like Henry's law or Raoult's law to find the mass fraction at this location. Okay, so that's our geometry. If we're going to say mass flux of A into the vapor, it's related to the total mass flux, because if we consider we have quiescent surroundings, there's going to be molecules of B there, but it's not moving. It's not moving across an area. So the total mass flux is, in principle, whatever's in the mixture, related to whatever's in the mixture. We have a mass flux of A and a mass flux of B. And in a lot of cases, you can use analysis where you can neglect any motion of B. So that's what the quiescent surroundings is using, that assumption. So the total mass flux is just movement of A per area. So for mass, so the mass flow rate, just m dot, is a function of r. But what we're saying is that in principle it's a function of r, but in this case it's constant because as the area changes with radius, it balances out by a mass flux of A. So this mass flux is changing as the droplet moves, and this area decreases in the case of evaporation, and those two counteract to give you a constant mass flux. Mass flow rate, this is just kilograms per second. So we can use that and then apply these to the species conservation. Which is tracking convective motion and diffusive motion across a volume. And for the assumptions we made, all these assumptions we made, plus this quiescent surroundings and so forth, you would be able to express this as the mass flux of A. There's no source term due to reactions, that's not here. So it's only this mass flux of A is related to this convective flux, which we have tracked as the mass fraction of A times the flux of A in the domain. That's the convective contribution. Then you have a diffusive contribution. This is the rho of the mixture and the diffusivity of the A molecule in B. So this is the Fickian diffusion contribution. That should be R. So this is radial coordinates. And then applying this assumption that we made here, when we want to keep track of, if we wanted to keep track of the mass flow rate, we can say that only A is moving. So the mass flow rate total is only due to A. And it's related to the mass flux of A here, as we said here. So plug all of that in, you would get negative 4 pi r. I'm running out of space here. Let me rewrite it. So the total mass flow rate equal, it's only due to the mass flow rate of A. Plugging that in, there's a negative sign. Combining all these equations, this is what you would get. So combining the mass flux and the mass analysis, you would get this. Applying this assumption of constant rho AB, So this is a separable differential equation. Ordinary differential equation, separable. So the boundary conditions are at the mass fraction of A at the radius, the surface, which is radius equals r surface. That's we define as this symbol here. And that is either a thermodynamic property or another correlation of mass transfer, which we'll talk about someday. And at the infinite, the far boundary at r equals infinity, you have a far stream mass fraction of A. Should be infinities here. Okay? So applying those, you would get the mass flow rate coming out of this droplet surface is a combination of all these and solving for the differential equation. Natural log so this, because it's only one component here, this is the evaporation rate. Applying all of these assumptions, which can apply to a variety of situations, you get this useful result. Depending on the mass transport properties of this molecule in the mixture, the density of the surrounding gas, mix, the radius of the surface at that moment, which decreases, and the far stream mass fraction and the surface mass fraction, which can, in principle, be found. Okay. So we can express this. I'll take away these assumptions here. We can use, define these new parameters to express this in a more compact form where these parameters kind of capture the physics of the situation. So we can define a mass transfer number. Let's call it By. Some mass transfer number as a function of the mass fraction as being the difference between the source of the mass, which is the mass fraction at the surface, minus the far stream concentration, the far stream mass fraction. So that's if this is driven by mass transfer, that would be kind of like the gradient, related to the gradient, and normalized by this surface concentration. So what this shows is that larger differences between this surface concentration, which depends on the properties of the liquid and the thermodynamic stability of the liquid, depending on that concentration relative to the far stream outside of the droplet, you would have more or less mass transfer. So the larger the difference, the bigger this mass transfer number. And so this can be kind of be thought as the driving potential for mass transfer. Why? Because if we, the way that we defined it, we're going to plug it into this evaporation rate, and the evaporation rate in terms of this mass transfer number So the larger this mass transfer number, the faster the evaporation rate. As we can see that it's proportional. As if this increases, the evaporation rate increases, and the way to have a larger mass transfer number is to have a larger difference between the surface and the far stream concentration. Okay. So let's get this into even more useful format. Here, so if we were to analyze for droplet if we analyze the conservation of mass of the droplet, we can get another useful expression. So applying that, it's also the evaporation rate. What it's saying is that the change in mass of the droplet with time is the evaporation rate. You're going to deplete the mass according to the evaporation rate. That's the starting point. And then, but you can also describe this depletion in mass using just the definition of mass and density, basically. The mass of the droplet equals the density of the liquid droplet, times the volume of the droplet. So that's the diameter, and which gives you the volume of the droplet. Multiply that by the density, you can get the mass that way. So by combining this expression we found with another definition of the droplet in terms of the diameter, you can show that another way of describing this would be that the change expressing the mass in terms of diameter, the change in the diameter with time equals negative So we combine this expression we found for the evaporation rate based on the species conservation. Then we express the mass depletion in terms of the density and volume. Combining those, you get another differential equation. This is also differentiable. And for convenience, mathematical expediency, we can use d squared. Why? Because the differential of d squared with respect to d equals 2 d dd dd. So canceling these out, we can write a more differentiable form. It actually cancels out the d. What it says is now you can write this as the differential of the square of the diameter is, so in terms of time, Okay, so we can solve that. That's a differentiable equation. We can bring the time to this side. That'll give us an easy integral. And if we were to let, okay, I'll do it up here. If we were to let, or define a new number, let's say K here, another mass transfer number, or evaporation number, this whole thing, this whole blob here, so the ratio of the gas to liquid density, the diffusivity of this mixture times this whole mass transfer number contribution, that whole thing, let's just call it K. K, just call it K. That'll give us the d squared law, which would be the way that we transform d to d squared, and just lumping these mass transfer parameters into one big monster K, you would get that the change in diameter with time squared equals the initial diameter of your droplet at time 0. I'll just call it, d naught. That's just t equals 0 squared minus kt. So all that for that. So this is the so-called d squared law of evaporation, which is that for some given transport properties of your liquid, you can estimate the time, the decrease in the diameter with this d squared law. So one thing that you're solving for is that asking the question, when does d equal 0? When is all of the liquid gone? That is d equals 0, and you can get a time at which d equals 0. That would be your evaporation, the lifetime of your droplet. So typically for droplets in the combustion world at least, typically is on the order of 10 to the negative 8 meter squared per second. And that will give you a characteristic lifetime based on the starting point of your droplet. So I don't have it written here, but the time of the life of your droplet, just do it on the fly here. The lifetime of your droplet would be when d equals 0, so it would be this 0, so yeah, it'll just be d squared over k. Your initial droplet diameter over the mass transfer properties will be the lifetime of the droplet, which is very useful general analysis that can give you can design spray nozzles and design if you wanted to inject fuel into an engine, this would give you some insight into a time scale for the evaporation process. Okay, so that's all I wanted to talk about today. Thank you, and I'll see you next time in the next edition of Learning Glass in Combustion. Thank you.